Hey, welcome back. Now we're going to do polar coordinates. So the regions we've been integrating over are often circular, and what happens is it's producing these crazy kind of square root things in all of our integrals, which is kind of annoying, right? So you're looking back at 14.2 at like our last problem. Um, we had all these square root stuff, right? Wouldn't it be nice if we could just get rid of those square root things somehow and simplify the integral? And yeah, it turns out that you could do a polar coordinate conversion, and things turn out to be a lot easier. So that's kind of what we're after in this section. You may want to go back and look at polar coordinates, graphing and polar coordinates in Calc 2. I'm going to introduce kind of the basics here, so just as kind of a warm up to chapter 14.3. Looking at some polar graphs. So first, remind yourself how the polar coordinate system worked. So in the xy plane, we could describe that point with x comma y. So, but we could also describe it with r comma theta. Okay, so this point, if this is some distance x and this is some distance y, and then we have this right triangle type region. Um, I could describe this point with a directed distance r and then an angle theta, where theta is this angle here. Okay, so how do I do that? Well, basically you can use trig, right? So if the distance of this hypotenuse of this triangle is the r, I could say that sine, actually let's start with cosine, right? Cosine is traditionally the first part. It's cosine theta equals adjacent all over hypotenuse. Okay, so we can solve then for x and get a coordinate conversion equation. So the first, for rewriting x, we can write it as r cosine theta, right? And then sine of theta is opposite over hypotenuse. So I could rewrite y as r sine theta. Okay. Then some other conversion formulas you might need, just from the Pythagorean theorem: x squared plus y squared is equal to r squared. And then also from the tan formula, tan of theta is equal to opposite over adjacent. So we just leave it at that. So it's basically these three formulas plus this one formula that we need to do all of our coordinate conversions. Okay. Okay. I just want to review quickly graphing some of these things. So I'm doing some graphing in the xy plane. First, an object like r equals 2. What the heck is that? Well, basically what you're doing is setting r to equal 2. So the arm on your kind of radius is always set at 2, and then theta varies. So in that case, you're just going to let that rotate around through all angles, and the object that is being drawn out will be a circle with radius 2. Okay, so 1, 2. Um, Likewise, if you're asked to graph something like r equals the region in between r equals 2 and r equals 3, r equals 2 is just a circle with radius 2, and then r equals 3 is a circle with radius 3, which will be drawn out like that. So the region between those two is this region here. Shifted circles, so I guess number 3, you have things like r equals 3 sine theta, or even r equals, we'll say, 3 cosine theta. Take a look at each one of those. So you could do a table of values, r theta values. Usually what I do is just draw it in the theta r plane. So 3 sine theta, amplitude is 3. Sine pi over 2 pi, 3 pi over 2, 2 pi. It'll look like this. Okay, so in the xy plane then, so this is the theta r plane. But in the xy plane, what I kind of do is draw out these little concentric circles to help me count on the r in the r direction, whichever direction I'm going in. And then the angles are rotations, right? So from 0 to pi over 2 on the r theta graph, it should draw out that. So on this graph in the xy coordinate system, going from 0 to pi over 2 it sweeps out that angle. Okay, and in that region, r is going from 0 to 3. So what's going to happen is it kind of curves out as it rotates and makes kind of a half circle. Okay. Then from pi over 2 to pi, this next region, where is that on the unit circle? Well, this is pi over 2, right? And I want to go to pi. So going from pi over 2 to pi, it's going to start at 3, and then as it sweeps out, as it will die down to 0. Okay. And then when it goes negative here from pi over, so just pi to 3 pi over 2, so in this region, the r values actually go backwards into the other quadrant, right? So if I'm in the third quadrant and my r values are negative, I'm actually back here in this quadrant. So as I rotate from pi to 3 pi over 2, it's going to rotate back onto itself, and it'll just end up rotating out on itself, and it'll come back around and it'll trace it out twice. Okay, you want to be a little careful with the tracing issue. So in particular, this circle is traced out completely from 0 to pi. If you go to 2 pi, you're over tracing, and you might end up over integrating. Okay, so we want to avoid that. Let's look at this other guy. So in the r theta plane, we're looking at 1, 2, 3, 1, 2, 3, and cosine, starts out at 3 and then dies down and then curls back up and then goes back like that. Okay, so in the xy plane now, it's starting out at 3 and then dying down to 0 at pi over 2. Okay, so here's 0, here's pi over 2. So the curve I'll do in red, it starts out at 3 right here. So 1, 2, 3 on the x-axis. You just count all the way over there. And then it dies down to 0 at pi over 2. And again, as theta rotates around the unit circle, the r value is decreasing, and it traces out this kind of circular half circle region. Then, so that was the first from 0 to pi over 2, and then pi over 2 to the pi right here, what's it doing? It's going negative. So rather than being in this quadrant, it's actually going to jump over here, and the r values are going to be on the other side. So you always think of kind of like an arm is rotating out. Okay, so maybe at like pi over 4, it's right here, and then pi over 3, maybe it's going in, and then finally at pi over 2, it's right here. And then as the arm rotates into the second quadrant, it goes on the negative side. So this is the positive side of the arm, this is the negative side of the arm, right? There's like two sides to it. So as I get into the second quadrant then, because if you look at the graph above here, you're in this region of the cosine function, I'm actually on the other side of the quadrant. So now the r values are negative, they're going to go into that quadrant. And so maybe this is 5 pi over 6 here, and the corresponding r value would be like negative 2 point something right there. But ultimately it traces out this circle in the second and fourth quadrants, and again it's going to trace out from 0 to the pi. Okay. Honestly, these are the most important functions, polar curves that you'll graph. The book will try to take it up a notch and throw in maybe some limnosons and some cardioids. I can kind of quickly remind you, I wouldn't expect you to be able to look at this and know the formula for it like they're asking you to do in example 1. But it is a cardioid, which is from the family of snails, the limnosons, French for snail. And in this particular case, the formula I wouldn't expect you to know just from looking at the picture, right? This is part C. They give you the formula down here, r equals 3 plus 3 sine theta. Let's see if I can go ahead and trace that out. And they're saying it's traced out from 0 to 2 pi. Okay. All right, so first I'm going to draw it in the r theta plane. So 3 sine theta, is 1, 2, 3, 1, 2, 3. I'll put it in red. So going by pi over 2's, it's going to look like this. And then if I add that 3 on there, it's just going to shift it up 3 places. So it'll kind of have a new origin or new x-axis. And then on top of that, I want to go 1, 2, 3 for the amplitude. So the new picture is going to go like this. And hit right there, and then go back up. Okay. So I'm going to draw that then in the xy plane. And again, you're thinking of an arm that is rotating around this unit circle, and you're literally counting out on these unit circles to get to you could graph points if you wanted to and graph this thing out. I don't recommend doing that though. 1, 2, 3, 4, 5, and then 6. Okay. If you wanted to, you can graph points. So this point, this point, this point, this point, this point. What are those points, right? So at 0, when the arm is at 0, so then the arm is sitting right here. And again, this side is positive. Maybe let's put the other side in red. This side is negative. Maybe red should be positive. I don't know. So anyways, on that arm, when theta is equal to 0, so this is your theta axis. This is 0, pi over 2. Pi, 3 pi over 2, etc. When I have theta is 0, I'm at 3 on the arm. Okay, so I'm actually count out 1, 2, 3. I'm right here. Then the arm rotates, right? So let's pretend it rotates to pi over 4, which is right here. Okay. There's the negative side. At pi over 4, it's going to be at about 4 point something. So 1, 2, 3, 4 point something, like right here. Okay. And then pi over 2, it's going to be at 6. So whatever the heck it's doing, as it rotates around here, it's tracing, and let's trace it in maybe green. I guess I apologize if you're colorblind. It's tracing this object so far. Okay. Then maybe at like 3 pi over 4 right here, it's going to go back to 4 point something. It's going to be symmetric in a lot of ways, so it's going to go and die down back to 3. 1, 2, 3 right here. Okay. And then so that's it rotating through the second quadrant with that arm right there. And then it finally finishes up at pi right here. Right? And then we want to rotate to 5 pi over 4 if you wish. At 5 pi over 4, it's more close to 1. So it's actually, as the arm rotates 5 pi over 4 here, the value, the point, is going to be on the arm at 1. So it's going to go like that, and then it's just going to die to 0. Right? At 3 pi over 2, it's going to be 0. So it's going to be like that. I'll stop doing green. It's like that. Okay. And then it's going to kind of reverse itself. So then it's going to jump back out to 1 and then hook up with the graph at 2 pi. And what you end up with this thing kind of looks like an upside down heart. Called a cardioid for that reason. All right, so I wouldn't expect you to kind of be able to generate maybe that object. It may come up in the homework, but on the test, I'm mostly interested in these sideways graphs, and then just the circles oriented at 0. So hopefully that's a review. If that's not enough of a review, you can always go to my Calc 2 channel and look at chapter 10.2ish about. So if you go to my channel, in my playlists, go to Calc 2. I guess they're not up right now, but if you want some, I can make them public and you just send me an email and say you want to see them, and the videos are in chapter 10. But you could look in your book at chapter 10.2.
Hi, today we're going to look at plane curves.
Whoops, it's actually 10.3 then. 10.3 would give you.
Hey, welcome back. This is 10.3.
Nope, 10.4. Okay, so then
So if you have that,
I go through the same thing with the coordinate conversion, and then I start working with polar curves and stuff like that. So this is actually Calc 2 stuff. I'm hoping you already know that, but if not, you can send me an email, and what I'm saying is I will send you a link to one of my videos. Okay, so let's move on to Calc 3, officially now 14.3, I guess. 14.3, and see what we're up against. Polar chords. Okay. So double integral in polar chords. Eventually we'll do triple integrals as well. We want to take a regular standard old integral. Maybe we could co-op a nice problem over here or something like that. Sure. So number 4. Well, no, I'll just give you an example. Okay, we'll get to the homework eventually. So let's pretend I'm to have this double integral thrown in my lap. 0 to the square root of 4 minus x squared, negative 2 to the 2, and I want to integrate the function x squared plus y squared dy dx. Okay, so let's draw the region. It's y equals 0, which is the x-axis, to y equals the square root of 4 minus x squared. So what the heck is that? Y equals the square root of 4 minus x squared. Square both sides, you get y squared is 4 minus x squared. Add x squared to both sides, you get x squared plus y squared is 4. So it's just a semicircle with radius 2. Okay, like this. And so y equals 0 to y equals this. Okay, and then curve the curve that to that, and then point the point negative 2 here to 2. So the region I want to integrate over is this circular region. And if I went and tried to do that, and I could, you know, it's just, it wouldn't be a lot of fun, right? Because your first integral on the inside there, you know, you're going x squared y plus y cubed over 3, evaluated from 0 to square root of 4 minus x squared. Already, my headache is returning, right? I gotta evaluate this antiderivative with that square root thing, and then I gotta take the integral of that, and it's just gonna be a nightmare. So what you want to do instead is convert to polar coordinates. And how does that work? Well, you use your conversion formulas first off for the integrand. Okay, so this junk in here I can replace with r squared, because if you remember our conversion formulas here, one of the conversion formulas said x squared plus y squared is r squared. Okay, so I can at least do that much. Okay, so I have r squared in my integrand, and then I'm going to have to replace this dy dx thing with something. Okay, and that becomes kind of difficult as well. So there's going to be something here. I'm not sure what's going there just yet. Okay, the bounds of the integral, though, I can think of in terms of a circle. So r equals 0 is just this point here. This circle here is r equals 2, right? So got the wrong color. Here's my arm that I rotate to generate that curve. Here's the point 2 on it, and if I rotate theta from 0 to where? I need to rotate theta from 0 to pi. So r is going from 0, which is just the point, all the way out to 2. And then I'm rotating this thing from 0 to pi, and those will give me the bounds on my integral. Okay, so all I have to do is kind of figure out that something. So what the heck is that something there? If you remember before, that something was the area of a bunch of rectangles. So we took this region and we would have crossed it up into a bunch of little rectangles. And so you would have like a change in x, change in y, right? And that would be your area. So for this one particular rectangle, the area increment would be like a change in x times a change in y. Okay. Now the regions that we're dealing with aren't exactly rectangles, so that's an issue. The regions we're dealing with now are kind of like pizza slices, right? So if we do our like polar graph paper, we're going to section it up into a bunch of regions like this, and then we're for our delta A, I need the formula for the area of these regions, and it's not just like a rectangle. You can't just go length times width. Okay, and not only that, it's variable. The farther you get away from the center, the bigger R is, the bigger these regions are. So it's not like figuring out the area of a square where these all squares are the same area. No, it's not going to work that way. Okay, so what is the value of just maybe one region here? And I think if we figure that out, we'll kind of have the something that goes right here. Okay, all right. What is that thing? Well, let's pretend the bottom curve here is R1, and then this top curve here we'll call R2. And then these two curves here we'll say are theta 1 and theta 2. Okay, then we're going to rename those. So I'll say R2 minus R1 is delta R, and then I'll say theta 2 minus theta 1, we'll call theta a change in theta, delta theta, right? All right, but anyways, what is the area of this thing? Well, you can get it from the area of a sector of a circle. So recall a circle and its area. Okay, so here's my circle and the area of a little sector like this. If I know theta and I know the radius, I can figure that out. It's a standing room only formula, SR theta. Okay, so in this circumstance, I kind of have this thing which I can figure out from the standing room only formula. So that blue wedge that I just drew out is whoops, and that's not the area, right? That's the arc length formula, sorry. So it's area equals 1/2 r squared theta. It's more related to the pi r squared formula, where theta is 2 pi. So when theta is 2 pi, you just get the area of the circle. I apologize. That's the area formula we need. Okay, so the first area, that blue wedge thingamajig, that part of it is going to be 1/2, I guess, R2, right? R2 squared. And then the theta is the difference between theta 1 and theta 2, which I'm calling it as change in theta. Okay. All right, so that's the blue area. I need to subtract away then this other area, which I'll put in yellow. This, and it's turning in the green. I need this area and subtract that away. So the area of that thing is 1/2 r sub 1 squared delta theta. Okay, and that thing right there is my delta A. I can't use it like this. I need to rewrite the heck out of it. So what I'm going to do is factor out the 1/2, factor out the change in theta, and I'll have R2 squared minus R1 squared times delta theta. I can factor that R2 squared minus R1 squared, and the R2 minus R1 times let's rewrite it the other way. R2 plus R1 times R2 minus R1. And now things are starting to come together, right? This first part is just the midpoint, okay? So we could just say that's some value R. And then R2 minus R1 is the delta R. And then the delta theta. And this thing right here is going to become the formula that we use. Okay, so that R becomes kind of like the midpoint that you would use back in Calc 1 when you were figuring out the area underneath a curve like this. So you could left-hand endpoints, right-hand endpoints are midpoints. The R is the midpoint that you're using in this version. And then you could take form a Riemann sum based off of this. But anyways, the sum thing is going to be, long story short, r times delta r delta theta. And it's a lot like the area formula. It's just as you move farther away from the origin, your little wedges are increasing in size. So you can see the wedge out here in blue is much bigger than the wedge inside here that I just so it's increasing by a factor of r, and hopefully maybe that will help you remember it's r d theta. Okay, that's what goes in there. And then you could integrate that, and it's pretty simple to integrate. So when all is said and done, it's not that big of a deal. So anyways, long story short, the conversion formula we have in general, the double integral of r of this function over this region r, we can integrate by doing this polar conversion. I'm replacing x with r cosine theta, y with r sine theta, and then we'll have replace the area increment with r d theta. Typically you won't interchange those limits, but there is an example in the book where you do, and it's just a matter of solving the r function in terms of theta. Okay, but anyways, there's sort of that idea, and of course we're going from some r function here, r1 of theta, to some r2 of theta, and then we're going from like theta 1 to theta 2, whatever those are. Okay, so let's attack the homework. Long story short, let's see what we're dealing with. It's just an r d theta thing, and you have to know kind of polar coordinates too. But okie dokie. So first problems are kind of just having it. This is a Rose curve. So if it's some cosine version of it, its amplitude is 4, so it'll be 4 cosine of 1, 2, 3, 4 pi 5 theta. I think it's this guy. Whoops, this guy. 4 cosine. Where is there a 4 cosine 5 theta? I think that's the answer. I hate it when it leaves me in suspense. What? Yes, I need you to log me out for some reason. Like somebody's gonna hack into my account and steal my answers. It's not gonna happen, buddy. Wants me to completely log in again. Hold on. Okay, sorry about that. So let's do some integrals, right? Let's see. Problem 3. So get the integral from 0 to pi, integral from 0 to 9 cosine theta, r d theta. So this one, they want to know the region you're integrating over. So it's going here, r equals 0 is just the origin, to r equals 9 cosine theta. So 9 cosine theta, its amplitude is 9. And it will start out at 9 and then dive down and then go back up. So it's going to start out on the x-axis over at 9, and then it's at pi over 2 it's going to drop to 0, and then from pi over 2 to pi it's going to increase back to -9, and you'll get this region. Okay, so from 0 to pi you just it's this one region from 0 to pi. This is pi. And it should just be this not that one. It's this guy here. Okay. They want you to integrate it. I assume you could do that, but let's look at one anyways. So with respect to r, it's r squared over 2 from 0 to 9 cosine theta, and these turn it into trig integrals. d theta from 0 to pi. So I'll have the integral of 81, unfortunately, halves cosine squared theta minus 0 d theta. You're going to do a power reduction formula. So 81 halves integral 1 plus cosine 2 theta all over 2 d theta. Pull out the 1/2, 81 fourths. integrate that thing, theta plus sine of 2 theta all over 2 after a u sub from 0 to pi is 81 fourths times pi plus sine of 2 pi is just 0, and then it'll be minus 0, so it's just 81 fourths pi. 81 all over 4 pi, I hope, you know. And yeah, okay, great. Let's keep going. This thing is just a wedge of a circle, so number 4. The integral from 0 to the pi over 6, the integral from 0 to 4 of r squared sine theta cosine theta dr d theta. So it's already converted. We just have to figure out what the region is from 0 to 4. Okay, so r equals 0 to r equals 4. R equals 0 is just this. R equals 4. So, 1, 2, 3, 4, if you wish. 2, 3, 4 is just a circle of radius 4. Okay. The only problem is theta isn't rotating from 0 to 2 pi. It's 0 to pi over 6. So where is pi over 6? By the way, it's just right here. There's pi over 6. So the region we're rotating out is this region, this wedgular region. And so that's going to be, it looks like this one. Okay. Let's make sure it's right. Yay. All right. Well, I need to integrate this thing now. So integrating it looks like an annoyance, but we'll do it anyways. First, with respect to r, so it's r cubed over 3 sine theta cosine theta from 0 to 4 d theta, and then 64 thirds sine theta cosine theta d theta. Do a u sub probably on cosine, so no, on sine, so you don't have that negative cosine floating about. So cosine theta d theta. So this is 64 thirds integral of u du. So you'll end up with 32 thirds u squared. U is just sine, so sine squared theta evaluated from 0 to pi over 6. Sine of pi over 6 is 1/2. So you get 32 thirds times 1/4 when you square it, minus 0, and of course that will be 8 thirds, I hope. Okay, so great. More of the same stuff. What is this region? 0 to the 3 and 0 to the pi over 2. So 0 to the 3 is here, and 0 to the pi over 2, so it's this guy right here. Okay, so now we're into actually evaluating iterated integrals. So number 6, 0 to 4, the inner integral 0 to the square root of 16 minus y squared. And we have 3y dx dy. Okay, so what you want to do is get the region and then convert to polar. Okay, so the region, what the heck is that thing? So it's going from x equals 0 to x equals this thing. Okay, x equals 0 is the y-axis. X equals square root of 16 minus y squared. So that's some sort of circle, right? So x squared 16 minus y squared, so x squared plus y squared is 16, and yeah, circle radius 4. But it's x equals 0 is this, the y-axis, and then the square root of 16 minus y squared is the right hemisphere of that circle. So it's actually this portion. And then we're not integrating from negative 4 to 4, right? It's y equals 0 to 4. So point to point is right there to there in this orientation. Right? So curve the curve, but then point the point is just this one region. So you want to be a little bit careful. Right, so on our integral, the r is going from 0 to 4, okay, to give you the circle, but they're only rotating from 0 to pi over 2. Okay. Then I want to convert everything to r d theta stuff, so y is r sine theta from our conversion formulas, and then you got another r from the r d theta. Okay, so this would be double integral 3r squared sine theta dr d theta now. So I just multiplied in the r. Then integrate with respect to r, so you get 3r cubed over 3, so the 3's will cancel. I just have r cubed sine of theta from 0 to 4 d theta. And so I'll have 64 sine theta minus 0, which is just 64 sine theta d theta. And then that'll be negative 64 cosine theta evaluated from 0 to the pi over 2. So that'd be negative 64 pi over 2. Cosine of pi over 2 is just 0. And then minus cosine of 0 is 1. So you're going to end up with 64 as your answer. Oh, they want you to fill it all in. So 0 to pi over 2, 0 to 4, 3. And I mean, this isn't bad because you can then check it to make sure it's right? 3. Oops, I forgot my r is squared because there's an extra r there. So you can submit and see if it's right, and then if it's right, go ahead and do your integral. And of course we got 64. Okie dokie, no big deal. So got another one. This one's a little different because it has a different orientation. For this one we do is dx dy. Let's try number 8. So it's going to be the other kind. Well, actually, let's just skip that to. Man, they're all making me write them in. I hate writing them in. Okay, whatever. So 0 to 2, and then integral 0 to square root 4 minus x squared, and we get the x squared plus y squared. This won't be so painful. 3 halves dy dx. Okay, get a picture. Okay, so it's going from y equals 0 to y equals the square root of 4 minus x squared. And of course that is just a circle of radius 4. Right, you square both sides, y squared, move the x squared over. Okay, great. So it's the top hemisphere in particular. The positive square root tells you it's the top hemisphere of the circle. So it's this portion. So I'm going from y equals 0, which is of course the x-axis, to y equals square root or whatever. And then on the x-axis, I'm collecting stuff going from 0 to 2. Okay, so point to point, that's actually from here to here. And again, we're only dealing with this one quadrant. Okay, so convert the polar, double integral, r equals 0 to r equals 4. And then I'm integrating theta 0 to pi over 2. And then do my conversions. X squared plus y squared is just r squared. And then r dr d theta. So I get the double integral. And I haven't forgotten the quiz question. We'll make that next. This will be r cubed times r is r to the 4th dr d theta. And so integrate that character, you get r to the 5th over 5 from 0 to 4 d theta. The integral of 4 to the 5th over 5, whatever that is, d theta. And that'll be 4 to the 5th over 5 times theta from 0 to pi over 2. And that'll be 4 to the 5th over 5 times pi over 2. I wonder if they just let me put it in that way. It's probably going to force me. Anyways, what are we doing? 0 to pi over 2, 0 to, I think it's to 2. Was I saying 4? Yeah, the radius is 2, buddy. So I screwed everything up because I put a 2 in there instead of 4. Or I put a 4 in there instead of 2. But the radius is 4. All right, yeah, so I'm okay. I mean, it's drawn wrong. That's what's wrong. I apologize. It should just be the 2. This should be a 2. Okay, so this should be 1 and then 2. And then it's yeah, 0 to 2. I should have noticed. I'm sorry. So that's a 2. This is 2. And then 2 to the 5th, 2 to the 5th, 2 to the 5th. So it would be 2 to the 4th over 5 pi. 16 pi over 5. I apologize. Okay, so what the heck was this thing? It was r to the 4th, maybe. Let's see if that's right. And yay! And then put in your answer. So we were saying 16 fifths pi. 16 over 5 pi. Okay, great. Let's make the next one the quiz. Kind of scrolling through to see if any of these are annoying. Okay, so later they're using the double integrals to figure out integrals in the plane, figure out the area of polar curves in the plane. Anyways, let's look at one of these characters. On this one, you need number 10. You're going to have to complete the square in that thing to figure out what the circle looks like. Maybe we should do that one. This one just looks like an annoyance, a serious annoyance. So let's try this one. Number 12. We want to rewrite it hopefully as one integral. Okay, so I got 2 over 2, 0 to x, xy, dy, dx, plus integral 5 root 2 over 2 to 5, 0 to square root 25 minus x squared, xy, dy, dx. Okay, so get the region as usual. The first region, you're going from y equals 0 to y equals x. Okay, so y equals 0 is the x-axis, and then y equals x is this curve. I'm going from 0 to 5 square root 2 over 2, whatever the heck that is. I'll just put it right here. And then for the next guy, it's going from square root 5 square root 2 to 5. Okay, so out here to 5. On the inside of the integral, you see it's going from y equals 0 to y equals circle with radius 5. So that's going to be kind of like this. Okay, so ultimately then I'm going from y equals 0. Let me put it in a different color if it'll allow me to. Y equals 0 to y equals x. And then the second integral, again, is going from y equals 0, but then y equals that square root 25 minus x squared, which is this circle right here. Okay. So your curve the curve, the first one, curve the curve is that thing, and then curve the curve on the second one is that thing. Of course, point the point would be that first, and then this second. Okay, this first, and then this second. Okay, so the region you're getting is going to be this kind of wedge. That wouldn't be that hard to figure out with using polar, right? Because it's just a circle rotated to pi over 4, I think. We want to make sure that's true, so we know what angle we get to use, and we need to kind of find the intersection between this circle and the line y equals x. So you could replace y with x and then solve this equation, 25 minus x squared. So you get x squared equals 25 minus x squared, so 2x squared equals 25, and x squared equals 25 halves, and this is where you're getting that weird 5 root 2 over 2, right? So square root on both sides, it'd be 5 over root 2, and then when you rationalize, you get the 5 root 2 over 2. So this point here, sorry, this point right here is at that frontier point on the integral that was originally given. So this point is 5 root 2 all over 2 comma, if you plug that into your formula for the circle, 25 minus 25 over 2 is going to be it's the same thing, so 5 root 2 over 2. But that's not going to matter, right? Because all we need to do is go to the polar coordinate system section, and the r value, then r is going from r equals 0 right here to r equals whatever the radius of that circle is, which is 5. So 0 to 5, and then we're rotating from 0 to this line right here. So what is that angle? I guess right here. It's going to be pi over 4. If you don't believe me, you can always just say, all right, this height right here and this length right here, right? So tan of theta is going to equal x over y. And I kind of already figured out those coordinates, and they're the same. So tan of theta is going to equal 1, so theta would equal pi over 4. So I'm rotating from theta equals 0 to theta equals pi over 4. And we get this nice integral, replacing x and y with r theta, r cosine theta, r sine theta. I'm going to get r squared cosine theta sine theta, and then r d theta. Okay, and that's 90% of the battle, right? So let's make sure we got it correctly set up. So pi over 4, 5. And then this is r cubed eventually. I multiply in the other stuff. Cosine theta sine of theta. Okay, let's make sure that's right, and then we'll integrate it. Yay. So integrating this character, r cubed, when I multiply these two together, will be, with respect to r to the 4th over 4. Cosine theta, sine theta, evaluated from 0 to 5, d theta. I don't know what 5 to the 4th is, but it'll be 5 to the 4th over 4 integral. I'll do a u sub on sine, again, to avoid the negative if I did the u sub on cosine. It'd be u sine theta, du is cosine theta, d theta. Okay, so I can just write u du, and that would be 5 to the 4th all over, so it'd be u squared over 2, so now all over 8, and of course u is sine theta squared, and then I want to go from 0 to pi over 4. Sine of pi over 4 is root 2 over 2. Squaring root 2 over 2 is the same as 2 all over 4, which is 1/2, so I get 5 to the 4th all over 16. Whatever the heck that is. 5. It's not going to let me put that in. So I got to figure out 5 to the 4th is. To the 4th, 625. 625 all over 616. Okay, great. Got some other ones. First octant, that means you're just integrating over, use double integral to find the volume of the solid bounded by the graphs. So the first octant is in that x, the first octant is this region, this sort of box region right here, okay? This box. So there's really 8 regions if you think about it. This would be the first octant. With the quadrants, they're kind of counted out in a weird sort of way. They go counterclockwise, I think. It's kind of weird that way for octants as well, but the first octant is usually, pretty much everybody knows, it's where x, y, and z, those coordinates are all positive. Okay, so you're in the first octant, you have x squared plus y squared is 9. That's a circle with radius 3. And then that's the region you're integrating over, so you're probably going to have a double integral from 0 to 3, 0 to pi over 2 of xy, which will become r cubed eventually, cosine theta, sine theta, and then dr d theta. We already put the r dr d theta, already put the r in there. So just kind of looking at it, I think that's how those will go. Anyways, the z equals 0 is just the xy plane for number 14. Let's look at one of these other ones. Oh, okay, so number 15, we kind of have an intersection of regions. Use double integral to find the volume inside the hemisphere given by that thing, and outside the cylinder given by this other thing. So the hemisphere is the upper half kind of circle here, and then you'll have whatever this thing is, the upper hemisphere. Okay. Then there's a cylinder kind of going through it, so maybe right here the cylinder is passing through it and going straight down, and then it will have like an opening down here. So there's my cylinder going through the thing. So what do I want? I want the volume inside the hemisphere, but outside the cylinder. So what I'm thinking is just find kind of the volume under the hemisphere over this region where the cylinder leaves a trace in the xy plane, right? So the integral, then the setup, and I could kind of take a look at the xy plane here. I want to do a double integral, so the r is going to go from 0 to whatever the radius is. Here they're giving you an a for radius. You're integrating the 64 minus x squared minus y squared, which you could rewrite as 64 minus r squared. X squared minus y squared, it's just r squared. When you factor out the negative, it'll be x squared plus y squared, so that's r squared. Then you get an r dr d theta, and then on the outer integral, you're going from 0 to 2 pi. You got to go all the way around the circle. That should give you the answer. Let's just make sure. I hate to send you out into the battlefield without any weaponry. But so we have a double integral of r. You just do a u sub on that, and that'll take care of business. R times the square root of 64 minus r squared, where r is going from 0 to a, and then we just do some other variable like t equals 0 to 2 pi. Okay. And so it's not going to let me. You guys are getting so cheap. Standard computation time exceeded. Let's make a 3 or something, and maybe it'll pop out and we can see it. It's not going to do that for me. It's not going to be so nice. Well, you're going to have to compute it anyways. I'm pretty sure that's right. We'll go ahead and compute it. So that u equals 64 minus r squared. Du is going to be negative 2r dr. So dr is going to be negative du over 2r. So we get the integral of u to the 1/2. There's a negative 1/2 floating around in here. There's an r. So du all over 2r, and that's negative, and then d theta. The r's cancel. You can factor out a negative 1/2 completely out of the integral if you wish. But anyways, u to the 1/2 integrated is u to the 1/2 plus 2/2, which is 3/2 times then 2/3. We have to remind ourselves to evaluate d theta. We're going from 0 to a, by the way. That'd be negative 1/3 integral of back summing. So I get, what was it? 64 minus r squared, then to the 3/2 from 0 to a d theta. So at 0, so what are we getting? Negative 1/3 integral of 64 minus a squared to the 3/2, and then minus 64 to the 3/2, which is going to be 8 cubed, right? Because square root of 64 is 8, and then I got to cube it. All this with respect to theta needs to now be integrated, so you're going to end up with negative 1/3 times, this whole thing is just a constant, so you can just write it as 64 minus a squared to the 3/2 minus 8 cubed times theta. And if you evaluate theta from 0 to 2 pi, you're just multiplying it by 2 pi. So you end up with 2 pi times all that baloney. And yeah, they want you to enter a number. Oh, they give you some more information. It's 1/2 the volume of the hemisphere. So that thing is equal to 1/2 the volume of the hemisphere. So I need the volume of the hemisphere then on top of everything, all my other problems. So the volume of the hemisphere then is just, you know, what do I got to iterate for this one then? So it's going to be square root of 64 minus r squared, r dr d theta. The total volume of it, so that would be from 0 to 8 and then 0 to 2 pi, right? Yeah, so you can kind of cheat your way to get the answer, because 0 to 8, if you put that integral into here, you replace a with 8. The other part of it then, so it says it's equal to 1/2 the area of the hemisphere, so it's negative 2 pi over 3 times 1/2 is negative pi over 3, and then you're plugging 8 in for a, so it's going to end up being times 0 minus 8 cubed, so minus 8 cubed. And then you're doing some solving, so multiply both sides by negative 3 over 2 pi, get 64 minus a squared to the 3/2 minus 8 cubed equals 3 over 2 pi. So that's going to give you a 1/2 times negative 8 cubed. And then that will be 64 minus a squared to the 3/2 equals negative 8 cubed all over 2 plus 8 cubed all over 1. Multiply top amount by 2, 8 cubes over 2. So that's just going to be equal to 1 8 cubed all over 2. Then you take the 2/3 power on both sides here. So you get 64 minus a squared equals this thing raised to the 2/3 power. So that's going to be 64 all over 2 to the 2/3, because 8 to the 2/3 is just 8 squared. So then you would get a squared equals 64 minus 64 all over 2 to the 2/3, and square root it, get a equals the square root of that thing, whatever the heck that is, 64 all over 2 to the 2/3. Okay, and 4 decimals, so we'll get that here in a sec. Gotta pause the video for a second. Okay, and yeah, that turns out to be the answer there. Oh, yeah, so a long road. So again, what you're doing is basically you find the volume over that inner part, right? And that's this integral, and then you set that integral equal to the volume over the outer part, which would be the entire volume of the hemisphere. So that red part that I'm kind of highlighting right there, that would give you the volume of the upper hemisphere. And then yeah, so you're setting basically this integral here equal to this integral over here, but you have to multiply this guy by a half. And rather than evaluate that one on the right, all I did was just substitute at the end. A is different, right? So the only difference between those two integrals is the one on the right has, well, a 1/2 in front of it, but also the upper bound on the inner integral is 8 instead of A. So it was quite easy to just then produce this equation, which is what both integrals on either side equal, and then solve for A. Okay, and it wasn't a pretty answer, but believe it or not, that turns out to be the answer. So still need to do a video quiz. I hadn't forgotten. So let's take one of these other types of problems for the video quiz. So I want to use a double integral to find the area of the shaded region. Here they're giving us a cardioid. So this is problem 16. This will also be the video quiz for the day. And this is video quiz number 3, I believe, and section I lost my video quiz sheet. Somehow I magically managed to lose it. Just 1 second. I think it was set number 7, right? I don't know what I did with it. Oh, this is so frustrating. Maybe it flew onto the... I gotta pause the video. All right, hold on. Sorry, I found it. Yeah, this is video quiz set number 7. This will be the third problem in the video quiz set. So this is problem 16 from WebAssign. So just let me write that down in my notes so I can check you guys off when you send in your work. Okay, so I need to use a double integral to find the polar region, and basically what that means is basically your innermost integral will just, the function is 1, like the height of this, if you make it into a three-dimensional object by kind of opening it up, you'll have a height of 1 on there, and then you have your r d theta, but the r value is going from 0 to 3 plus 3 cosine theta. I guess the real issue is kind of figuring out the outer limit here. I believe it's just going to be 0 to 2 pi, but I literally have to sit there and graph it to make sure, which is kind of a bummer, right? So anyways, let's take a look at the graph. 1, 2, 3. It's a cosine shifted up 3, so this would be kind of the new x-axis. 1, 2, 3. And starting up at 6 and then diving down and going over 4. So like this and like this and like that. Okay, so in the xy plane then I'm starting out at 6, so I can get some circles. 1, 2, 3, 4, 5, and then 6. And I start out at 6 right here, and then from 0 to pi over 2 it's dying down to 3. So 1, 2, 3 is like right here, and then it dies down to 0 at pi, so right here, and then it increases back to 3 at 3 pi over 2, so 1, 2, 3 right there, and then it's going to increase back to 6 right here. Okay, so yeah, it's from 0 to 2 pi, long story short. So we can go ahead and integrate that character. Let's do that and see what we get, right? So yeah, it's kind of a bummer. You really have to graph them out. I don't know why the calculator can't figure out it's just too hard of a problem, I guess, for it to figure out. It is weird. But anyways, yeah, you're integrating r first with respect to r, so that would be r squared over 2. From 0 to 3 plus 3 cosine theta. d theta, and that's going to be a bit annoying, but we can do it. It'll be foiling the 3 plus 3 cosine theta when you put it in for r squared, so it'd be 9 plus 9 plus 9 is 18 cosine theta plus 9 cosine squared theta all over, I guess it's just 2, right? It's just 2. I'm going to have to do a power reduction formula on this character. So I'm going to get integral, let's factor out the 1/2, right? Well, we better not, because it's going to just, I can see into the future. 9/2 plus another 9/2, sorry, 18/2 for the second one. I don't know why I thought that was 9/2. It's just going to be 9. 18 over 2 is 9. 9 cosine theta plus 9/2 cosine squared theta, but we're replacing cosine squared with 1 plus cosine of 2 theta all over 2. And then we're going d theta, and then you can kind of butterfly that fraction and then combine like terms. So you would have 9/4 plus 9/4 cosine 2 theta, all that d theta, but I gotta smush it in there. I don't know what's going on sometimes. It won't let me smush it in. Okay, I'm sorry. So combining like terms, this is 18/4 plus 9/4 is 27/4. Integral of plus 9 cosine theta plus 9/4 cosine 2 theta, and then that's d theta. And then you'll have 27/4 theta plus 9 sine theta plus with a u sub, you'll get a 1/2, so 9/8 sine 2 theta, and then we're going from 0 to 2 pi, which shouldn't be very painful, because sine of 2 pi and sine of 0 are both 0, so you're just going to end up with 27/4 times 2 pi, so that would be 27/2 pi. Okay, I hope, right? So 27/2 pi, and submit. Yay, and we got it. Okay, so this is more of the same. So that was a video quiz question. This number 18. All right, so you got to find the area of that, and it's an area of 2 regions, right? So this could be a bit difficult. So I have r equals 1, and then a circle of radius 2. So r equals 2 cosine theta. You're going to start out at 2 right here, and then it's going to create this circle like this. And they're trying to get you to find the area. Sketch a graph of the region bounded by the graphs of these 2 equations. So the common region is going to be this region right here. Okay, so you know, okay, so it says inside the circle r equals 2, and outside the circle r equals 1. Okay, so the eraser button was on, and I just erased everything. So again, the question says inside the circle r equals 2 cosine theta, so that's in this part, and then outside the circle r equals 1, so they want this stuff here. Okay, alrighty then. In order to figure that out, it's not maybe as obvious as I think you would think. Yeah, so use a double integral to find the area of the region. So I'm going to cut it in half first off, because I can tell it's symmetric. So I can start with r equals or theta equals 0 to theta equals whatever the heck this point is. Okay. The curves, you could put those on your inner integral. So you could set it up with the 2, or rather the r equals 1 is on the inside right here. is kind of your inside curve, and then the r equals 2 cosine theta is this outer curve right here. Okay, so it's going to be going from r equals 1 to r equals 2 cosine theta. Okay. Then the issue is just figuring out whatever the heck this angle is, right? So it's going to be where those two graphs intersect. In other words, where r equals 1 and cosine theta. Yeah, so I just have to solve this equation. You just set the r's equal to each other. 1 equals to 2 cosine theta. That'll be 1/2 cosine equals cosine theta. And in the first quadrant, that means theta must be equal to pi over 3. So you're going to pi over 3, and then of course it's just 1 dr d theta, and I'm dying to know, make sure that's correct so I can sleep at night. So I'll cheat a little bit. Please don't do this yourself unless you're really on your last try. So what do we have? I lost my r. I need an r in here. R dr d theta, right? So it'd be r integrated from r equals 1 to 2, we'll just say cosine of x, in parentheses, comma, then x equals 0 to pi over 3. And hit the machine and see what it gives me. Root 3 over 4 plus pi over 6. Let's see if that's right. Square root 3 over 4 plus pi over 6. And then pop that in and see what we got. I'm heartbroken. All right, hold on. Could it be I just forgot to multiply it by 2 because because all I was doing was going from 0 to I hope that's it. Let's hope that's all it is, right? So this would be pi over 2 and then pi over 3. Come on. Sweet. All right, so there's that. Sorry the video is so long. I'm sorry I stumbled through a lot of those exercises. As usual, thank you for watching, and I will see you next time.